sphere and shell. A conducting sphere of radius a and charge plus q is surrounded by a concentric conducting shell of inner radius b and outer radius c. The outer shell is first grounded, then the grounding wire is removed. Using Gauss's law, determine the electric field in these four regions, then develop an expression for the electric potential difference between the surface of the sphere and the inner surface of the shell, so that's this area here. Then develop an expression for the capacitance C of the system, and finally a liquid dielectric kappa equals 7 is filled into the space between the surface and the shell as shown in the shaded area. Here's our liquid dielectric in here. What is the capacitance of the new system in terms of the original C? First, we have to figure out where the charges are. So we will start with the shell not connected to the ground and determine what's going on. We have a plus Q on the sphere. That will attract a negative Q from the outer sphere into the inner surface here. And why is that? Well, if you do Gauss's law, inside a conductor, the electric field is 0, so the enclosed charge has to be 0. Therefore, if there's a plus Q on the sphere here, there has to be a negative Q induced on the inner surface of the outer shell. So we have the negative Q there. However, initially, the outer surface was uncharged. It has to stay neutral by conservation of charge. Therefore, the negative charge that came inside here has to be balanced by a positive charge on the outside of the shell. So the total charge of our system is still plus Q, which is where we started. We then ground the shell. The outside of the shell will attract negative charges from the ground until it is neutralized and its total charge is 0. The inside of the shell will still have that negative Q charge which balances the plus Q charge on the sphere. And that's a consequence of Gauss's law and electrostatic equilibrium for conductors, where the electric field within the conductor is 0, so it must enclose a net charge of what? 0. So on the outside of our shell, we have Q equals 0. On the inside, we have a negative Q, and then we have a positive Q here on the sphere. The ground is then removed. We still have the plus Q on the inner sphere. We have the negative Q here on the inner shell, and we have 0 charge on the outside of the shell. The negative charges picked up by the outside of the shell from the ground remain there. There's no path back to ground, and they neutralize the original positive charge. Now we can proceed and calculate the electric field at the various places now that we have the charges all figured out. For r less than a, that's inside a conducting sphere, so there is no charge within the sphere. So when we apply Gauss's law, the integral of E dot dA is enclosed charge divided by epsilon 0, and electric field is 0. Find the electric field between the sphere and the shell. We draw a Gaussian surface. Here's Gauss's law. We have E dot dA simplifies to E dA. We pull the electric field outside. We integrate over the sphere, and that's 4 pi r squared. Our enclosed charge is plus Q. That's the original charge on the sphere. So the electric field between the sphere and the shell is Q over 4 pi epsilon 0 r squared. Find the electric field within the shell. Gauss's law one more time. But what do we have here? Here's our Gaussian surface. The enclosed charge is 0. Therefore, the electric field is 0. And also from knowing about electrostatic equilibrium, conductors have no electric field within them, so we have two ways of saying this. But it's all coming from Gauss's law. Finally, we want the electric field outside the shell and sphere combination. There's our Gaussian surface. The enclosed charge is plus Q minus Q. It's 0, so the electric field is 0. That's a consequence of having first grounded the shell and then removing the ground. Develop an expression for the electric potential difference between the surface of the sphere and the inner surface of the shell. Here's our equation that we're going to use. The electric field in this region here is kq over r squared. We integrate in the radial direction, and we're going to go from b to a. The integral of negative 1 over r squared is just positive 1 over r. We evaluate it between a and b, do a little algebra, and here's our potential difference between the sphere and the inner surface of the shell. Find the capacitance of this system, and that's going to be Q over difference in potential between the sphere and the shell, this area here. We plug in the value of delta V from the previous slide, and we get capacitance is AB over K times B minus A. We now have a dielectric on the bottom half of the sphere-shell combination down here. We need to find the capacitance of this system. We'll call the top capacitor C1 and the bottom C2. So we have two virtual capacitors here. The top one has no dielectric and the bottom one has the dielectric. They're in parallel since they have the same voltage drop. Right? The voltage here compared to here is going to be the same. Each capacitor also has half the area, yet they have the same separation D of the original capacitor. So the original real capacitor here, epsilon 0 A over D, when we form C1 and C2, D stays constant, but each only has half the area of the original. We'll work with C1 first. That's the one without the dielectric. So C1 is epsilon 0 A1 over D1. D1 is the same as the original D. The area is cut in half, so the capacitance of C1 is epsilon 0 A over 2D. Now go to C2, the bottom one with the dielectric. That's going to be kappa epsilon 0 A2 over D2. Once again, the distance is the original distance. The area is half the original area. And here's going to be our capacitance of the bottom virtual capacitor. Since these two virtual capacitors are in parallel, to find their equivalent capacitance, we just add them together. So we have epsilon 0A over 2D plus 7 epsilon 0A over 2D. We do some real simple algebra. We get 4 epsilon 0A over D. And who is this? That's your original capacitance. So the new capacitance is 4 times the original capacitance.